we have with us Mr. Robert Mains. So welcome to the final talk, and we really hope that you've had a great time thus far, and our last talk is just the cherry you need on top, because Mr. Rob Mains is a 40-year industry veteran and currently the general manager of Chips Alliance, which is part of the Linux Foundation. Rob is a former engineering vice president of Oracle and Sun Microsystems distinguished engineer, where he led an organization of over 200 software researchers and developers. Prior to this, Rob was a principal engineer at Magma Design Automation and originally a senior engineer at IBM, and was involved in numerous technical areas for the development of IBM Super and S390 systems. He is the holder of 13 US patents. In this talk today, he will explore the overall hardware development ecosystems, how it is evolving from a proprietary niche arena to a democratized community of contributors across the spectrum of hardware and software development. So over to you, Rob, for your talk titled Building the Open Source Hardware Ecosystem.
Thank you very much, and I appreciate the kind invitation to come and chat with you all today. So let me start my screen share, and hopefully you can see my title slide. So the title of my talk is Accelerating Beyond More. You know, what's required to help us get to the next part of the innovation ecosystem. So about myself, as mentioned, I have about 40 years in the industry. I was a vice president of a fairly large organization of design enablement, as the term is typically used. And I learned that from my colleague, Cliff Ho at TSMC. But what design enablement really is about is building an entire platform that an engineering design team can use to build a chip. And this is particularly important relative to new process technologies, where there's a lot of challenges in terms of understanding what the technology itself does, and then the tools to properly design and verify the chip before you actually send it off to be manufactured. So I have both a bachelor's and a master's degree in computer science, and I will say this, having been in the industry a long time, that change is the name of the game. There's always something new coming down the pike, some new challenges you have to go deal with, which makes it exciting to say the least. So this is kind of a funny chart. I was thinking about this yesterday, really. And, you know, technology in many ways, it's kind of like it has a half-life of a piece of fish, right? Or you could also say, is that really planned obsolescence? And that concept of planned obsolescence came from Alfred Sloan of General Motors. I think it's more, though, than that, though. Building these new chips, if you will, or process technologies is huge investments based for companies, right? It costs billions of dollars to actually build the process technology. It costs that much to do, or significant amount of money to build software to help design the chips. It costs significant money to actually do the architecture development, to refine the instruction set architecture, say for like a CPU. And then finally to get it out into product takes a long time too. So there's lots of money involved, lots of IP. It's really a technology treadmill, right? That's what keeps this thing going. And the question is can we accelerate more to keep Moore's law going? That's the real challenge that we have. And so as you can see here, technology decreases in value quite rapidly, just like a piece of fish, if you will. Not maybe a good comparison, but I think everyone understands what I mean. So looking at the chart, so we've all benefited from the technology scaling that we have seen over the past 50 or 60 years, right? It's allowed us to do much more, if you will, or encompass more function on a given piece of silicon or chip than what we ever thought possible. And we've benefited all from this. We've been able to take existing designs, map them to a new technology node, and get better power performance area as a result. But that is starting to run out of steam, certainly in terms of building 7 nanometer, 5 nanometer, now 3 nanometer, and even down to 1 nanometer from research being done by IBM in upstate New York and by others around the world, such as at TSMC and Samsung. We're seeing that this is getting more and more difficult. So there are other techniques that can be used. One is in the area of packaging. So one type of package called a multi-chip module has existed for a number of years. There was also earlier times a thermal conduction module, TCM, that was used with bipolar and actually had chilled water running through it to cool it. And more recently, we've seen something called AIB, which is a chiplet type technology that, amongst others, is being promoted by Intel and in part as Chips Alliance, but allows for different functionality to group closer together. Separately from improving CPUs and instruction set architectures, as was mentioned earlier, talk, which I happened to catch the last bit of, we also see different types of accelerators coming into existence. In other words, to provide offloads for traditional CPU work specializing for a particular area. The most notable, of course, being the GPU, but perhaps, which is used both for graphics and artificial intelligence, but of interest being from Oracle is the database acceleration unit, where actual database queries would be handled by a specialty type of processor within the main Spark core, which is what Sun and Oracle were using. And of course, then there are FPGAs, which are programmable gate arrays. Those too can be embedded a chip or could be a sideboard to a CPU. And those can handle customized types of instructions as based upon the loading that's put into them. And finally, and unsurprisingly, but maybe not known by everybody, but both compilers and the underlying software libraries have a significant impact on the performance. If those two are not tuned and improved for a given software architecture or computer architecture, they will actually kill you in terms of performance. So those are both very important aspects of building the entire ecosystem. But the question is all of this enough to keep us going, or do we need to do something different? So if we look at where we've been going in industry, we're really going from what I call a soups to nut type approach, where a company does everything internally. This could be represented by companies such as General Motors and Ford in earlier times in automobile manufacture. It was certainly the case for both IBM and AT&T in the 70s and 80s, where they had their own foundries, they had their own EDA system, they had design teams, they had packaging, they had the whole thing. To where we have evolved to more now in some regards, where we are supply chain management or just-in-time delivery, which was a concept originally pioneered by Toyota, where all the manufacturers were in close proximity to the main manufacturing plant. But if you look at companies such as Apple, and also relative to like Qualcomm, what we did at Oracle, and even IBM too, we're dependent upon others to provide us different things, whether that be EDA or the actual chip process technology that we want to use. So that's a different type of relationship. But what we're moving to now more is an area called open collaboration. And what this allows for is what I would call is disruptive innovation, by letting folks from different areas participate in the development of new technology or new ideas. And it's also another way to modulate R&D spend and non-refundable engineering costs, which is effectively what R&D spend in chip development is typically called. So this is something that we're starting to move into and is helping us to accelerate into the next step. It's disruptive thinking from where we have been in the past. So if we look back in time, in terms of the evolution of software, many of you may recall, years back, and this is going way back, there with punch cards, code was typically assembler, which is machine level code. You could do things in octal, right? You could actually punch things in octal codes. There were flowcharts, line printers, terminals. There were very simple text editors, VI and Emacs, and then debuggers, DBX and GDB. And many of these things are still in use now. But there's been a big change in the past 20 years or so, or even 30 years. And that's going from a traditional procedural type approach to object-oriented. There's object-oriented software design. There's a plethora of productivity tools. You can write it once, it can run it anywhere. There's reusable software components that you can use to help build things very quickly. Tons of libraries that you can pull upon to create your functionality. And I'll just say it's fun, right? It's just really exciting that you can go out and get all this stuff. You can build things. It's great. And the net out of this is that you're accelerating innovation, increasing productivity, and it takes less people to do it compared to years past. So just providing some background on Linux Foundation, right? So in the early 90s, as some may recall, we had many operating systems, right? There was the VAX VMS operating system. There was IBM mainframe. There was Solaris. There was OS/2. There's Windows 95. And then there was something that just kind of showed up called Linux. I remember the first time I heard about this, I was sitting in my cubicle in Austin, Texas, working on PowerPC for Apple. And a young engineer worked for me, came in and says, "Hey, I got this thing called Linux. It's really cool. You should check it out." I was running AIX, of course, on my workstation. I thought it was crazy. Well, guess what? It wasn't. That was the start of a revolution in the software industry. And now we're looking to take that into the hardware arena. So the Linux Foundation, just as background, it's much more than Linux. There's about 1,500 members from 4 different countries. All the Fortune 100 companies are involved in this. There's over 30,000 developers. There's over 2 open source projects. So it covers a wide range of different technology, from security, artificial intelligence to motion pictures. You can see that there's quite a wide range of technology that this is covering, and also healthcare of time as well. And it really has spawned a collaborative open source initiative, right? So we have about 12 million lines of code being added weekly. There's about 32,000 different contributors that participate in this. It really provides a way to look at different areas and provide many eyes on different problems than was ever possible. You can never achieve such a thing in a company, no matter how large it is. I recall a time back at IBM where you could always find the person within the IBM who would know the answer to a question. And that was true of all large companies back in the day. Now it's a community of contributors and knowledge experts who you can go work with to find answers to hard problems. So the question I think everybody's probably asking, well, what's about hardware? You know, it's a very different business. I think I heard earlier about the mention of the company Ansys, and I'm certainly familiar with those in some of my background, and also some of the other major EDA players, right? So it has traditionally been a very closed ecosystem, right? So the question is, does this need to change? Can it change, right? So we are in a revolution, one amongst many over history, but suffice to say we are on the brink of bringing out 5G hardware as an example, advanced computing and healthcare type initiatives. And these chips are in everything that we touch and do. It could be in your toaster oven, certainly is in your cell phone, in your watch, on your arm. You know, it's projected to be over 100 billion different things by the year 2050. So in open hardware areas specifically, the Linux Foundation, there's Open Power, there's RISC-V, and there's CHIPS Alliance. And so CHIPS Alliance right now has 37 different members to date, has a combination of companies such as Intel and Google, Antmicro, Alibaba, Xilinx, which is now AMD, but also a number of leading universities as well. And we come together and we collaborate on different problems. And just this one chart here shows that the success of open hardware is growing, as exhibited by RISC-V. And specifically in terms of RISC-V growth, you know, there's projected to be 62 billion cores by 2025. And the significance of this technology has been validated, if you will, by a huge investment that Intel Foundry Services has just made in the RISC-V ecosystem, which is a real stamp on open source design and development. And that's what they are working towards to help accelerate. So specifically, the question may be, what is CHIPS Alliance about? Well, at the heart of it, what it's really about is creating an open design ecosystem, all the way from specification to RTL, to process design kits, EDA tooling, the physical implementations of that, and standards. So it's a broad spectrum of what we're trying to do. The overall goal, though, is to provide an open innovation across that wide spectrum. And it's comprised of many different participants. It could be individuals, universities, foundations, industry, as examples. So one question I get typically is open source process design kits, and is there interest in this? And in fact, there's a huge interest in this. So when Skywater Technology open sourced its process design kit for 130 nanometer process technology in conjunction with Google and its sponsorship, the number of downloads of that technology increased significantly, as seen here in the far right. And this really comes back to simplifying the overall business model or the legal model for people to try things out. You don't have to go through a lengthy legal process. And I can tell you from personal experience doing this with my foundry partner, TSMC, for new process technology nodes, that certainly was the case, right? It would take weeks, if not months, to go through all the different legal agreements. So by open sourcing this and making this available, easy for people to use, is a huge difference. The question then, though, is, well, what about sensitive IP, right? As I mentioned earlier, foundries do invest significant amounts of money and engineering time into building new process technology. So working with some of my partners, we do have ways to do this, right? We have different types of what we call umbrella type of agreements, right? Whether it be for yellow IP, which might be for something like a 12 nanometer process technology, to red IP, which could be more like a 7 or 5 type of nanometer. But basically, it provides an umbrella NDA that allows for collaborative participants to work. And also, it can be formulated under a secure cloud or container-based design environment that protects all the different participants and the IP associated with that. And it also works with what I call obfuscated API or software structures to help obscure the details of the underlying process technology such that it is safe. So what is, collaborative design really about, or how's this going to look? So, this is kind of a simple diagram, but effectively, if you think of a chip design, it's similar to like a software architecture of a hierarchy or a tree that typically what has been historically has all been in-house, right, which is represented on the left. In the middle, which is more where we are today, some of that IP may be purchased. It could be brought from a Cadence, a Synopsys, or other IP provider, right? What we're looking at in the future, though, is that some of that IP, instead of being purchased or built in-house, it will be open source. It will be a trusted ingredient that you can pull into your design, and it's good because it's been validated by the community. So what this really is talking about is enabling design use or reuse or interchange. So there's soft IP, which I think the prior chart does illustrate in some regards, right? You're replacing a given library, if you will, with IP from an open source area. But it could also be hard IP, right? It could actually be a physical implementation that you are picking up that is implemented in a given process technology node. There's also the notion of chiplets, as I mentioned earlier, which effectively allows you to pick different elements or things that you want to put into your overall package to instantiate your IP. So it really broadens the overall ecosystem of what you can possibly do with the product that you want to design, and allows for innovation beyond that. So let's just take a look at some of the examples from CHIPS Alliance that we are doing in a collaborative fashion. So I mentioned earlier, or just in the other chart here, about the AIB chiplet interface, which was donated by Intel. So I think the big thing about this is that it really establishes both a protocol and the electrical aspects of the signals between these different chiplets. So these different interfaces, AIB leader, AIB follower, can be placed upon a given chiplet or chip and then put in a higher level package. And this greatly simplifies the effort for a community if you're a business trying to build something, you can pick these things up. And there actually are businesses that are doing just that. So what I've shown here, though, is that there's effectively a menu of different IP that you can use or pick up and use to build higher level functionality. So you may have your own part. It could be an FPGA where you can dynamically decide what you're going to do, if you will. But then it can be comprised of other different chiplets that are available in the marketplace and allow you to pick that as in the ecosystem. So that is definitely something different than what's ever been available from what I have seen. Another area that CHIPS Alliance is working on is called OmniExtend. Basically, this is a cache coherency protocol that we're working on with Western Digital and other participants, and RISC-V as well, which effectively is to make the data center the center of the architecture. Enables collaboration of the family of different processing units. So you can have a RISC-V, you can have a power core, GPU, FPGA, all types of different things as part of this. So there's really no established hierarchy, and the cache coherency is preserved over the network. The other aspect is that there's an entire RISC-V ecosystem out there. This was provided in part by Western Digital again, but effectively what they have provided is both the open source RTL implementation for a swerve core, as I call it, which is a RISC-V based core set with the associated peripherals around it, and then have provided the necessary verification bench with it to help verify the design. And this will work in conjunction with a Verilator, which is an open source functional simulator, or others if you license a proprietary one. So this also is another way for enabling companies to pick something up that has been verified and built in silicon and use that to build new product. So let me talk a little bit about EDA, because this, as was mentioned, is certainly a challenge area in terms of providing disruptive innovation. So one of the things that definitely is ongoing, right, is the notion of hiding complexity and increasing productivity, right? So, if you look at the left-hand side, years back, designs were done entirely in transistor. They were hand-tuned, they were placed, the layout was done, manually routed. It was with the notion of the long, tall, thin designer, right, where a designer would own the entire portion of their design from transistors up through gates and into verification. We then went into gates as a first level of abstraction, right, which simplified the problem somewhat. And then we moved into RTL, which is more like a hardware version of assembler language. So that's the best way to think about it, is that you're describing your design in assembly code, and which was represented by design languages such as Verilog or VHDL. But what we're seeing now is that people are taking more of a software approach, right? So that's helping to broaden the participation ecosystem. Python is one of the languages that is actively being used for hardware description. It's object-based, there's library services, there's ease of reuse and integration verification, right? And finally, then that can be compiled or built down into the actual transistors, which is similar to what compilation does in the software world. Again, the overall idea is to accelerate innovation and increase productivity. So CHIPS Alliance is doing active work in this entire area to help make this a reality. So again, the theme here is to make hardware more like software. This really is part of the democratization process of hardware design. It's basically is to encourage others to participate in it, make it fun, if you will, to help alleviate the fear of failure. So by providing different types of languages, whether they be Python, System Verilog, System C, or Chisel, it really helps expand the designer productivity. So Chisel is based on Scala, for those that don't know, which is an object-oriented language. It comes out of, Chisel itself work comes out of UC Berkeley for reference. But again, the idea is to expedite designer productivity, provide libraries of function, and really to orient towards object-oriented thinking, and then provide the necessary tools or compilation mechanisms to go from that language into the actual representation in gates and transistors. This is a somewhat detailed chart, but I just wanted to share this a bit, that this is the steps that one goes through in terms of translating a design from the programming language into actual gates. So it goes through a process called logic synthesis, which takes in these different technology files. You'll see the process design kit there. You'll see the standard cell library, which is a representation of transistors into logic function gates. Goes through synthesis, place and route, logic or physical extraction, which is the delays associated with each of those, and then through different types of electrical analysis. So this process will iterate a number of times until you get to the point where the design is electrically and physically correct. And that will then have GDS, which is a physical design description of it that gets sent to manufacturing. Similarly, at the same time, in parallel, the design language description will be synthesized and will then be placed into different types of simulators for functional verification. A key part of this, of course, is using FPGAs for soft verification, which allows for a rapid iteration of the design with the actual software code that you're trying to write. So that's a great increase in the overall productivity loop from what we saw in the past, where formerly you would have to wait for silicon to come back from manufacturing to test out your software. You can now do that in an FPGA much more quickly. And there are a number of different participants in providing this software in terms of research and development. And much of this comes from the university world, such as the Berkeley Analog Generator, which is from UC Berkeley here in California, where I live. It's also in terms of the work that University of Minnesota is doing in terms of Align, and also University of Michigan, which is FASAC, which is taking more of what I call a structured approach to analog design or cell-based analog design, which also improves time to market productivity. On the digital side, a lot of work has been done in terms of the development of the place and route system, which is similar to what I showed in the prior chart. This has been funded by DARPA from the US government under Professor Andrew Kong at UC San Diego. And that's being used extensively now for digital place and route. And so all of these things here help greatly accelerate the time for development. And just as a reference for those that don't know, time to market and development time is important, because if you think back to the chart that I showed earlier relative to the lifespan of technology decaying quickly, the faster you can get something into actual product is equivalent to the improvements in technology that you see over time. So if we put this all together, what we're talking about with CHIPS Alliance, and what we're trying to do is to create an open design enablement environment with a catalog of trusted ingredients. So this means an open source verified and trusted IP component library that is comprised of both logical macros and physical macros, as well as a cell library and the necessary verification test bench that goes with it and the functional simulation to make that happen. And then correspondingly, for the physical implementation, the necessary analog tools and digital tools to make that happen as well. So that's what we're trying to do, is we're trying to build this entire ecosystem for participants in the industry to effectively use to build their design. So one question that was raised is, I will readily admit that this entire area has its own set of jargon and terminology, which may not be familiar to everyone in the audience. And I apologize if I've confused folks by that. But one question was, what is a chip tape out? Well, the best way I think about a chip tape out is similar to what one has seen in the Apollo 13 movie, where the flight commander in NASA in Houston at the time asked each team if they are ready for the launch, right? So that's what a chip tape out has historically been like, right? It's basically, is everything signed off and ready to go? There's an entire checklist of different things that you go through and look at and make sure that you've ensured that is ready to be sent to manufacturing. And the reason for this is that manufacturing times, particularly for modern process nodes or the new nodes, can take months. So you want to make sure that when you send it, that it is both functionally and electrically correct, because making a change after it's already gone into manufacturing can be difficult, if not impossible. Doing an ECO after the fact, again, is an expensive process, right? So those are things that we're trying, historically have been trying to do. Now, we're trying to change that level of thought. So I will say that, this has, in some regards, in the chip design community, has created a level of paranoia, right? Before you tape it out, it's like, gosh, did I do this? Did I do that? Et cetera. We're trying to simplify that. And we're providing quick shuttles, open MPWs or multi-process wafers, we're allowing, enabling the community to move away from that type of thought process, right? That you can change things quickly, right? And do it on the next wafer. So there's like a regular train of these that we're trying to do and get rapid turnaround. So this makes a big difference, right? And this will disrupt the community. And this is kind of similar as to what's happened in the space program, right? We went from, all government funded type of efforts and initiatives in space program to now we have commercial things like SpaceX or Blue Origin. So it's really a change of thought process and difference from where we've been in the past. So just some challenges with open source CDA software. Of course, one is, first off, is technology access, right? So fundamental information is required, frequently does require an NDA. I will say that the major foundries though are getting much better about providing this. The Open Road folks, as an example, do have agreements with some of the leading foundries to have access to their process design kits, which does enable them to update their algorithms for that. So that's definitely an improvement. I will say that the developers in EDA, it's a unique mix of hardware and software skills. It typically does require some type of detailed knowledge in a highly specialized area, such as routing as an example, static timing is another. Another key aspect is testing, qualification, and quality results, right? Regression testing and QR are key parts of the development process. And the qualification to foundry data is a key aspect, right? So in other words, when you do a static timing analysis of your design, you have a given path through the design. How well does it correlate to the actual underlying hardware, right? So that's another key aspect of it as well. And then of course, there's just the overall methodology and support. In other words, if there's a problem, and there's always a problem, right? That just always the nature of the game. And it usually occurs at the worst time, like on a long holiday weekend, and you're under the gun to get a chip out the door, so to speak. There's an issue. You need somebody to call, right? So that's another challenge with open source CDA software. Who's that person going to be? And it's also about building trust, right? It's more than just having open source IP and application catalog, right? You need to have confidence that something is going to work. So, I worked for an executive vice president of Oracle, and that was his thing. Whenever I went and would go in with some new idea or something, it's like, I'm the one who has to sign off at this at the end of this day. How can I trust this to know that it's going to work? So that's what it's really about. You need to build confidence and trust, right? And that's where the hardware IP, that's a key part, right? It's going through the tape out process, productization confidence, making sure that things work properly. Same thing for EDA applications, right? You have to know that it correlates properly, that the extraction is correct, that it adheres to the design rules, that they are proper. So there's many different aspects to this overall ecosystem and making sure it's proper. So again, summing it up, what we're trying to do is build an open source model for IP plus your innovation that helps build product. And so there's many different collaborative aspects that we've been working through. And hopefully this will help differentiate and revolutionize the overall ecosystem and help us move forward. And there's also certainly business opportunities here for folks to start companies. We've already seen new companies in this space, right, that help embody the developer community through the open source community repository. And that allows for different service companies to build upon that, to release that different product, whether it be IP for chip design, or if it be EDA as representative examples as well. So in summary, open source hardware verification and tooling are here. They're gaining momentum. It's going to help us accelerate even further beyond just what Moore's law can do for us. You know, hardware engineering is learning from software, right? So concepts of abstraction, object-oriented design, libraries of functionality are becoming much more prevalent in the open source ecosystem to help us move that much more faster. Companies, universities are collaborating on mutual challenges of interest, and business models are evolving as well to help change the way things have been done in the past, to go more towards a services type of company to provide support for open source, similar to what Red Hat did with Linux. And companies are now innovating at higher levels, leveraging open source IP, which helps them to accelerate their time to market. And CHIPS Alliance, as part of the Linux Foundation, is really providing the collaborative platform to help all of this happen. So that concludes my talk. If there are any questions, I'd be happy to take them.
Thank you so much, Mr. Mains, for your talk. It was particularly interesting to us because we really believe in that open source and collaborative innovation. In fact, over here, we do use Chisel. And
very good.
So yeah, I mean, it struck quite a few chords with us over there.
Oh, very good.
We do have one question for you in the Q&A box. I'll read it out for you.
Oh, thank you. Go ahead.
May I? Yeah.
Yes,
is
please.
Omnix in any way related to the Omnix, that is an accelerator-centric OS? So
not that I'm aware.
Yeah.
Not that I'm aware of.
Yeah, the naming was so close together. I do have one question also. Over the last 2 days, we heard many different approaches how to the next era of computer architecture. And I think what all of them had in common, it will become more complex. It won't just get smaller, it will also become more complex. We talked about optics, we talked about in-memory processing. What you were just presenting feels to me like the reasonable, necessary answer almost to this, to handling the complexity and having more of a community approach. Is this unavoidable, or do people in the industry have a different thought or a different approach?
I think there's growing realization that there is a need for community participation on these complex problems. And I approached a colleague at an FPGA company here the other day, and they have traditionally been closed source, if you will. In other words, it's their IP. They are not going to, they'll just share the end product. But the executive indicated that they are definitely seeing the need to bring in a community, a collaborative community. And, it's the old saying, the more eyes you have on a problem, the better you are likely to solve that problem successfully. And certainly, as part of Linux Foundation, as an example, that's the belief relative to constructing secure systems, whether that be software or hardware systems, that the more eyes you have on the problem, that the more robust solution you are going to have as a result. There's always going to be fear or concern that bad actors could become involved, that could disrupt things in an unfortunate way, or also that your business IP, if you will, could be taken and stolen, if you will, right, and used. But our belief is that by having more eyes looking at a problem and offering solutions, the better the solution is going to be, the more robust the solution will be.
Thank you.
We have a question from Harshal. Is there in the chat? What should be the first few?
Okay, yes. I think the best, so that's a good question, right? And so I frequently get that. I think the best way really is to look at participating in one of our work groups, which an organization does not have to join CHIPS Alliance. You don't have to necessarily sign any legal agreements up front. You can kind of try before you buy, so to speak. So we have work groups in analog design. We have work groups in FPGA. We have verification work groups. You can participate and see if it fits the needs of your company or organization. And then at that point, you can join CHIPS Alliance. You can go through the contributor level agreements, right, that one typically signs to join CHIPS Alliance, and go from there. So it's definitely a easy path to entry, if you will. Other questions?
There's more and more in the Q&A window. What examples of intermediate open source hardware deliverables which others can build upon?
Well, I think, excuse me, I did cover that in part relative to the RISC-V core is certainly an example of an open source hardware that already does exist out there, both in terms of the actual instantiation, but also in terms of the RTL, the design description that you can pick up and use to build different things. There are certainly other examples as well that are available out in the GitHub repository that CHIPS Alliance has, and whether that be actual design or verification suites, as example.
Those were all the questions we had today.
Okay.
So thank you so very much for taking the time out and delivering this talk. And this was pretty refreshing because this was tackling the problem from a completely different aspect. So thank you so much for that as well.
Thank you.